today's lesson, we're going to be talking about how we find inverses of functions. This is something that you learned in 9th grade integrated algebra, and we're going to kind of expand on that today. So what happens when the domain and the range of a function trade places? The special trade that we're talking about creates something called an inverse. It's the inverse of a function, which is what we're going to talk about in today's activity. So on the following page, we're going to see some data about a wind tunnel and an experiment on wind friction and resistance of an automobile at varying speeds. It gives speed in miles per hour and resistance in pounds. So let's take a look at the next page in the data. Notice that our domain is our speed and our range is our resistance. What we're going to do on the next page is we're going to create a scatter plot so that we can view this data and how it relates to each other. So Control I, you're going to go to Data and Statistics, which is choice 5. Speed was our domain, so that's going to go on our x. And our range was resistance, that's going to go on our y. Notice that when we graph this, it gives us a very nice curve. Now this, if we wanted to put in a correlation or a regression line, we would choose exponential. But right now, we're just going to look at it for what it is. All right, so if I wanted to look at what the inverse of this function would be, I would want to see this domain and range switched. So what I'm going to ask you to do is just click on either the x or y axis and change the label. So from resistance, instead of resistance, we're going to look at speed. Notice how it takes that curve and it kind of makes it go in the opposite direction here. It's going from convex to concave, we could say. All right, so what this is actually doing is this is reflecting for us. And the line in which it's reflecting over is the line y equals x. Okay? So we've already done this slide. We went back, we changed the domain and range. We did it without changing our table. We did it just by switching the domain and range on the scatter plot. All right, so how does the arrangement of the new data points compare to the arrangement of the original? Well, what happened was our domain and our range were switched. Or our x and y is another way to say it. Okay, also, it showed a reflection over the line y equals x. All right, so domain and range get switched, or our x and y values, and also shows a reflection over the line y equals x. So all of these are ways to look at the inverse of a function. All right, on the following page, you're going to graph y equals 2x plus 3, and we're going to identify the ordered pairs where the line crosses the x and y axes. Once we do that, we're going to take those points, we're going to find the inverse of them, and plot them on the graph using our point on tool. Okay, so 2x plus 3, we're going to hit Control I, graphs in geometry, 2x plus 3, graph that. We want to find our x and y intercepts. It looks like our y-intercept is at the point 3, 0. Our x-intercept is at the point negative 1.50. I apologize. 0, 3. I'm skipping ahead on us. Okay, so here are our 2 points. These are the intercepts. So what I'm going to ask you to do is find what the inverse of these 2 points are. Okay? The inverse of the point 0, 3 is 3, 0. The inverse of this is 0, negative 1.5. So now what we're going to do is we're going to plot those points on our graph using our point on tool, which can be found in our menu. So I'm going to go menu, points and lines, point on. The inverse was 3, 0, so we're going to put a nice point on 3, 0. Once we click the point, we hit enter so that it holds. Our next point is negative 1.5 here. Click enter so that it holds. Okay? Since we no longer need that tool, we're going to hit escape to get rid of it. So now we have our 2 points that are going to be on our line that is our inverse of 2x plus 3. Now I want to create a line. So what I'm going to do is I'm going to go to my menu. I'm going to go down to points and lines. And then I'm going to choose line. The way I create a line is just by clicking on each one of these, and what will happen is a line will appear. Okay? So there's our line. Notice that this line intersects with the original or the parent function, okay? It's the inverse. So if this is the inverse, it should be a reflection over the line y equals x. So what I'd like to do now is actually put in the line y equals x to see where that lies. So Control G, x, enter. So there's our line y equals x. So that says if this was paper, I could fold that over on that line and they would touch. Notice where the intersection is. The intersection of the parent function and its inverse intersect on the line y equals x. Okay? All right. What is the equation of the line that resulted in switching the x and y coordinates? All right, so our points were 3, 0, and 0, negative 1.5. Now, we can find the equation of this line by using something called point-slope formula. Y minus y1 equals m times x minus x1. Oops, went a little crazy there. Okay, so in order to use this formula, we have to have the slope. Slope formula, of course, is delta y over delta x. So we're going to very quickly find our slope. Negative 1.5 minus 0, 0 minus 3. We get 1.5 over 3, which, of course, we do not deal with decimals and fractions. So when we do this out, this gives us 1/2. So there's our slope. Our next step is to plug in the rest of our information into our equation. And we, of course, want to use the equation that's going to be the easiest for us to simplify. So we're going to use this point here. You get y minus 0 equals 1/2 times x minus 3. When we distribute this out, you should get y equals 1/2 x minus 3/2. This is our inverse, the line for the inverse. The other way that you're going to see this written, and I prefer that you write it, f to the negative 1 of x equals 1/2 x minus 3/2. This means the inverse of f of x, the function f of x. Okay? All right. So let's go ahead to the next page. If you need to pause it here to get this work done, go ahead and pause it. Okay, so how would we do this algebraically? Well, the way that we would do this algebraically is the same way we would do it if we were dealing with just a single point. If I gave you the point xy, the inverse of the point xy is the point yx. So we're going to follow along with that when we deal with equations and doing it algebraically. I've got y equals 2x plus 3. So what we're going to do is we're going to take our x and y and we're going to switch them. And then we are going to solve for y. So we're going to subtract 3. So we get x minus 3 equals 2y. Of course, if you feel more comfortable in writing it this way, feel free. It's the same thing. Divide everything by 2. We get y equals x over 2 minus 3/2, which, of course, is the same thing as the last equation that we just built using point-slope form. Okay? So this is the algebraic way of finding the inverse of a function or a line. Okay? All right, let's take a look at the next page. Okay, so far we've observed two functions and their inverses of those functions. And in both cases, the inverse and the original pass a vertical line test. And as you know, the vertical line test tells us that something is a function. So the original is a function, the inverse is a function. Another way to say this is that the original function passed both the vertical and the horizontal line test. When this happens, when it passes the horizontal line test, we say that it's 1-to-1. And what 1-to-1 means is that for every x, there's one y, and vice versa. In order for a function to have an inverse, f to the negative 1 of x, there's that notation again. In order for it to have an inverse, it has to be 1-to-1. What that means is, if it doesn't pass the horizontal line test, it can't have a function, or it can't have an inverse, I'm sorry. Okay, so if it does not pass the horizontal line test, it does not have an inverse. Okay, and we'll look at some higher ordered ones a little bit later on. All right, so to obtain the inverse of a function, the domain and range trade places. Well, yeah, reflect the graph of the original function across a special line, that special line being y equals x. That's true as well. Switch around x and y in the original function, or all of the above. Well, of course, we know that every single one of those works, so the solution is all of the above. The inverse of a function is always a function. Agree or disagree? I am going to go with agree. Okay, so that's just a little checking of how you're doing. All right, so these are some extra problems. A, B, and C on the right are the original. The ones on the left are the original. The ones on the right are the inverse. What I'd like you to do on your own time is to solve these out and see if you get what they get. Okay? All right, next page. So what happens when we want to find the inverse of an exponential function, such as y equals b raised to the x power? Well, the inverse of an exponential function is a logarithm. Okay, so we're going to start learning about logarithms today. All right, our general rule is as follows. If I have y equals b raised to the x, then the way we change this, it becomes log base b of y equals x. Okay, y equals b to the x, log base b of y equals x. So my base for my exponent here becomes my base for my log. Notice it's what gets sat on here. So if I had a table, it would have to settle here. My exponent sits on top of it. So b is the base. The exponent is what it's equal to. B is the base. The exponent is what it's equal to. And then our single number here is going to go in those parentheses. Okay, so it's just a matter of getting used to how we rotate these things around. Okay, so how do we write in logarithmic form? Now, 25 equals 5 squared is the same thing as 5 squared equals 25. Okay, same thing. We can write it either way. So what you're going to do is you're going to change this into logarithmic form. Basically, what we're doing is we're taking the inverse of this exponential function. So log base 5 of 25 equals 2. This is how we change from exponential into logarithmic. Okay, so take a minute to do the next three. Pause here if you need to. When you come back, the solutions will be on the board. Okay, so you notice for the first one, all we're doing, again, that base becomes the base. The exponent is what it's equal to. So this is you just have to practice it. It takes a little bit of practice to get used to it. Now notice for the third one, I didn't write a base. When you have a base of 10, it's what we call a common logarithm, and you do not need to write the 10. Okay? All right. I bounced around? Oh, I'm okay. All right, to evaluate logarithms, we can write them in exponential form. So now we're working backwards. Now notice this first one isn't equal to anything for us to finish it. So what we're going to do is we're going to simply set it equal to x. That way we have something that we're looking for. Okay? We're going to very quickly change it into exponential. We get 8 to the x power equals 16. Now, of course, you guys know that our Inspire does this for us. We can very simply put in log base 8 of 16 and get a solution. Okay? So what I'd like you to do for these next two is put them into exponential form. Pop the original into the calculator to see what the solution is. Okay, so these next few we should have gotten 64 raised to the x equals 1 over 32, and 9 to the x equals 27. Okay, now I'm going to let you find the solutions to those on your own. All you're doing is popping them in. So this is going to disappear on me. So if I needed the solution, all I'm going to do, I've got log base 8 of 16. I'm going to Control-I, add calculator page. Log base 8 of 16. We're going to pop it in. Our solution is right there. Of course, 1.3 repeating is the same thing as 4/3. Okay? All right. Common logarithm is a logarithm with the base 10. We just discussed that. No need to write it. All right, so let's take a look at how we graph a log function. On the next page, I have the graph of y equals 10 raised to the x. On the same graph, I want you to graph the function y equals log of x. So Control G, y equals log. Oops, sorry about that. So here's our function. Notice that my original function, my parent function, or my original, is 10 raised to the x. The inverse, because we know the inverse of an exponential function is a logarithmic function, is log base 10 of x. Now, if I were to put in Control G, y equals x, there's the line it's reflected over. So again, it's a reflection over the line y equals x. Last page, I'd like you to graph this, and I'd like you to graph its parent function as well, which is y equals log base 6 of x. And I want you to look at and see how this has been transformed. So I'm going to very simply copy this, Control C, Control I, add graphs and geometry, Control V to paste, hit enter, Control G, log base 6 of, no, I forgot what it was, x. There's the original. So I'm going to put the equations of the two up there. Here's my first one. My original is the bolded one. Notice when I subtracted 2 from the x, it shifted my graph 2 units to the left. When I added 3 to the entire logarithm, it shifted it up 3 units. So that is how we transform these graphs. Okay? For those of you that are in Mrs. Cucci's class, just so you know, you have a quiz next class. Weekly project 9 is due next class. And your extra credit project, if you're choosing to do it, is due on the 11th, January 11th. So I suggest you get those in and done. Another reminder, midterm, January 21st or 22nd, depending on which day you have me. So start studying